what is the vector? As you can see, there is multiple ways we can deal with the vector representation. First one is, suppose let's for an example we'll consider to plot this b vector 1 minus 2 in a 2D space. As you can see here, we have two components for this vector v, and when we plot this in a 2D space, this is our x-axis, this is our y-axis. We go 1 unit towards x-axis and minus 2 towards negative y-axis, and this is the plot 1 minus 2. Similarly, we can have a plot of 2, 3, 5. This will happen in 3-dimensional space. X, this is y, this is z. We go 2 units towards x-axis, 3 units towards y-axis, 1, 2, 3. The intersection of both the planes, it is here, and we go 5 units towards y-axis, 3, 4, 5, 1, 2, 3, 4, 5. It is somewhere down the line here, 2, 3, 5 vector. This is the vector u. So here you can clearly observe, for a 2-dimensional space we have two components, 1 and minus 2. For a 3-dimensional space we have 3 components, 2, 3 and 5. So this is a 2-dimensional vector. U is a 3-dimensional vector. And another, what is the unique property between v and u vector? They both are column vectors. So how do we represent these column vectors and row vectors? There is an alternate format. Let me get to it. This is a column vector. We can write in this format also, 2, 3, 5 transpose. These both have same meaning. So as you can see, this has 2-dimensional vector. This is a 3-dimensional vector. So what happens if both column and row vector is represented as the same dimension? So you can see here we have represented a column vectors with component v1, v2, v3 up to vn. The size of this column vector is n cross 1. Similarly, for the row vector, we have represented this component u1, u2, u3 up to un. The size of this row vector we have represented as 1 cross n. Now let us see what is this. Which of the following multiplication is possible with the vectors having same dimensions? Out of these 4 options, you have to choose which possible case has the possible multiplication. This one, this one, this one, or either this one. If you clearly analyze all the 4 different cases, you will get 4 different results for different cases. Okay, let us go one by one. We have considered V as our column vector, U as our row vector. If we remember, in the previous slide we have considered v1 v2 up to vn. If you take the transpose of this column vector, it will be represented in the row format, and you are multiplying with another row vector. Both would are having same size of 1 cross n and 1 cross n. Similar is obtained from here also. This is u is our row vector, transpose will represent it in the form of column fashion, and v is our column vector. Both are having n cross 1 and n cross 1 size. But ask yourself, are we able to multiply these vectors for both these cases? The answer is no. From the linear algebra point of view, you need to have column of first vector should match with the row of the second vector. Here n is not is equals to 1. Similarly here 1 is not is equals to n. These two are not matching. These two are not matching. So here multiplication rule fails. So the result does not exist. Similarly, for the case 2, v is our column vector. We have taking one of these transpose multiplication with its original format. Here, as you can see, it is the size of this vector is 1 cross n. The size of this vector is n cross 1. Here the column of this vector matches with the row dimension of this vector, so multiplication is possible. So the final result is this: v transpose v equals to v1 square plus v2 square plus vn square. So can you guess, is it a scalar result or a vector result? Which one of this is the result of v transpose v? The answer is scalar. Okay, vector is, it's not a vector, it's a scalar. As upon multiplication you clearly have seen this matches with this, so our output will be a 1 cross 1 result, dimension result. Similar happens for this case also. U transpose with the multiplication, we have taken 1 cross n, here it is n cross 1. It is a summation of all the n dimensional components, so our u transpose u is having this result. This is also scalar. Okay, let us go to the third case. Here v is our column vector, v transpose will represent as the row vector. If we keep on multiplying one component with the entire vector, we end up getting a matrix. What is the size of this vector? It is n cross 1, and the size of this vector is 1 cross n. The column and row matches, so we are having a n cross n matrix. Similar follows for this also. U transpose u, it is having n cross 1 and here is 1 cross n. Upon multiplication we get a n cross n matrix. These are the diagonal elements of this matrix. u1, u2, 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 u1, un are the diagonal elements of this matrix. Last case, u times v transpose and v times u transpose. U is our row vector represented with the size of 1 cross n vector. V transpose is represented in also, it is a column vector, but V transpose make its representation as a row vector of size 1 cross n. Similarly, these are not satisfied, multiplication rule fails, so it is the multiplication is not possible, the output result does not exist for this case. Similar with this case also, V is our column vector of original size n cross 1, this is of n cross 1. U was supposed to be a row vector of size 1 cross n. Upon taking transpose, it becomes n cross 1. The column and row does not satisfy, so multiplication rule fails here too. Multiplication not possible. The result does not exist for this case. So we have considered all the four cases. Okay, out of which we have gotten this is a scalar result, and here we have obtained a matrix result for this case. Okay.